And last week we got started with thinking like a geologist, but we should first ask the question, what is geology? And of course, geology is the study of the earth, its physical properties, its substance, and the various structures that are contained. Here we have some images such as some canyons, some sandstone structures. We have a beautiful image of Half Dome here, and it looks like some geothermal plants for geothermal energy on a mountainside. So, of course, geology is the study of the Earth, our planet that we live on. And why does geology matter? The previous slide showed an image of geothermal energy. So, of course, there are some natural resources and energy relationship with why geology matters. The images that we see here are some images of various natural disasters, such as volcanoes, lava flows, and landslides that we see here. But of course, there's many different things. So, for one, we want to understand the history of the Earth and how history would repeat itself. So, the direction of that the Earth is going towards. Currently, we're undergoing some climate change, or previously it was called global warming. There is a slight energy crisis now where we have a finite source of oil and gas and various resources that we are currently mining out of the ground. That is not infinite. So our resources eventually will run out, and to have a better understanding of geology will help us, one, find out more locations for additional resources, or perhaps a shift towards a different type. We want to take care of our knowledge of geology for water conservation, how much groundwater that exists, and how to keep a clean water source. And of course, the various natural hazards. So, clearing up the topic of geology, we go into this week's lesson plan, which is plate tectonics. So plate tectonics is still a relatively new idea if we compare this against math or physics. All right, so plate tectonics developed somewhere in the 60s, and this was a combination of various ideas and various researches that combined together to form into plate tectonics that we know of today. So one of which is the fitting of the land masses, where they would fit like puzzle pieces. We see here in current day the globe, we see that there's a near perfect fit with South America and Africa if we were to essentially remove the Atlantic Ocean. And through geologic history, the study of it, we are able to determine that there are similar fossils and rock types between those two continents, South America and Africa, which further supports that those two were once connected. So if we go ahead and rewind the clock, we could see that eventually at some point in time, we'll end up with this large supermass continent called Pangaea that many of us may have heard of before. So the shifting of the continents are attributed mainly to, or half to, the mid-ocean ridges. Right, so the mid-ocean ridge is located in the mid-oceans. So here we have the mid-ocean ridge located between South America and Africa. And what a mid-ocean ridge is where we have the magmatic upwelling that drives fresh hot magma through the oceanic crust, and it creates new rock. So when we create new rock in the very center where it splits the oceanic plate, it pushes all the old rock further away from the ridge. So that's shown by the two arrows moving in opposite directions. So as it does that, it essentially will move everything that is located on the plate further away from that mid-ocean ridge, so furthering the gap between South America and Africa. And this is what's called a seafloor spreading, and we know this exists through some various studies of paleomagnetism. So what happened is we would have ships and subs, and we would be measuring the Earth's magnetic field as we cross the major oceans. And we noticed that there's a polarity shift every so often that would give the oceanic floor kind of a barcode, right? Where there's north and south oriented minerals that are located in the rock. And these orientations occur when the hot magma is brought up between the mid-ocean ridge and cools. So as the magma cools, the minerals will align with the current magnetic field. And with Earth's history and time, we know that the Earth's polarity will flip. So North Pole will be the South Pole. So in a magnetic sense, the magnetic North Pole is located in this magnetic South Pole location. So that means the minerals that would cool from the hot magma would be aligned to that present day magnetic field. So as we create new oceanic crust and the old rock is pushed away, we end up with this band where the minerals will be oriented 180 degrees to one another. And where we have the new crust that's being formed from the mid-ocean ridges, where we have magmatic upwelling creating new crust and pushing the old crust further away from the ridges. And eventually that crust will meet a different material, such as the figure that's shown in the lower left, where we have oceanic lithosphere in contact with the continental lithosphere. And when these two meet, one is more dense than the other, so the oceanic lithosphere is more dense than the continental lithosphere, which means the oceanic lithosphere will subduct. It will take a dive under while grinding against the continental lithosphere. So those X's that are shown there are representations of earthquakes. And this is rather deep. So no human has physically been able to go to that subduction zone and go underground and observe this event occurring. But we know that it happens based on the earthquakes and the study of earthquakes. So in seismology, where we study earthquakes, we're able to properly locate and pinpoint where each event happens and all the various aftershocks. So if we're locating these various earthquakes, we're able to create this map in three-dimensional space of each individual earthquake. And if we were to create a kind of a layer out of these points, they will line up into a very nice flat plane. And that plane is essentially the contact point between the oceanic crust and the continental crust as they move and grind past one another, creating these very large earthquakes. And as it takes as the oceanic crust further subducts into the mantle, it starts melting and breaking up. And this destruction of the oceanic crust creates more earthquakes, which are then pinpointed. So now we'll move into a hotspot. So a hotspot is essentially that on an oceanic crust. It is a centralized point of extreme heat because of this mantle plume that is coming up and drilling a hole through the oceanic crust. And when that hot mantle plume breaks through the oceanic crust, we start having an underwater volcano. So as that hot magma that comes up and cools underneath the ocean, it eventually builds and builds and builds until we have a above surface volcano. So we'll have this active volcano for some period of time until the oceanic plate moves because of the mid-ocean ridge current constant generation of new oceanic crust. So that oceanic plate will move, and that hot spot being in the exact same spot, that same location, will move to a new part of the oceanic crust where it hasn't drilled through yet. So it'll continue that cycle, and we'll have the series of volcanic island chains. So after several millions of years, we'll have what's known as the present-day Hawaii. And we've touched about on these different boundaries, but we haven't explicitly talked about the names yet. So in the mid-ocean ridge, where we have new crust being formed and the two plates on either end being pulled apart, they are diverging. So they are divergent boundaries. In a subduction zone, where we have the destruction of plates, so we have the two plates that are colliding. They are converging, so they are convergent boundaries. And in a convergent boundary setting, it does not necessarily have to be an oceanic continental convergence. It can be an oceanic convergence or a continental convergence as well. And finally, we have what's called a transform boundary, and this is a side-to-side motion. So there's no two plates being pulled apart or being pushed together. They are merely passively sliding against one another. So they are just transforming the surface landscape by sliding. So with all of these, what was discussed earlier, seafloor spreading, the magnetic polarity flip in the oceanic crust, the earthquakes that are measured and detected on the subduction zones, the hot spots, and the fossils and rock distributions on different continents that are separated across by an entire ocean. Because of these various evidence and research that has been done on these all combined and created evidence for what we now know as plate tectonics.